Here I am explaining you the paper that is smart scheduling of heat through reinforcement learning. Okay, so let's start here. This paper is about scheduling of electric vehicles, and it is mainly using deep reinforcement learning technique in the artificial intelligence for actually scheduling and controlling the home appliances and scheduling of electric vehicle charging at home. So this paper mainly has two components. One is the home, here like this. The home is equipped with solar panel and energy storage. It is also connected with the grid, and the home contains different type of appliances which are being monitored by the reinforcement learning agent. The homes are also equipped with electric vehicle charging stations that are low power charging station, around 7.4 kilovolt charging stations that can be added in the home for the purpose of charging EVs. So the objective of this study is to apply deep reinforcement learning algorithms such that we can control the generation to the load management actually overall. So when we in this we have this photovoltaic generation coming from the solar panels, and then this generation is also here with from the grid, utility grid that is being built. So our purpose is to schedule the whole setup, schedule the incoming energy in such a way that it is appropriately distributed into the battery and also to the EV and import and export without compromising the comfort of the user. Here the load is managed appropriately. So for that purpose we are designing this agent. Let us go to the introduction and check that what we are actually going to do here. Here the first thing is the photovoltaic generation that is on the rooftop. This will maximize the renewable energy usage. So we will optimize, the objective number one is to optimize the home appliances in such a way that the consumption cost is minimum, so that we have minimum electricity price, and we can without compromising the comfort of the user. This whole system is actually data driven. That means we will be using some real world data set for actually handling the data. And for actually handling overall system, I mean modeling the solar panels, then modeling the home appliances, modeling the battery, and also modeling the electric vehicle charging. We are using a model-free deep reinforcement learning approach. That means we are not given any kind of conditional model of the agent or the home where we have to take the decisions. So it is a model free that we have to learn through a random distribution, so that we can try to reach an optimal policy. Here the decisions that are in the hands of reinforcement learning agent are the charging of batteries, then discharging the batteries, and scheduling the appliances and EV as well. Also, import and export are also the decisions of the agent. These are called mainly actions. So in this session, we will cover this coding of this paper mainly. I am introducing this paper to you for reference, and we will be mainly discussing the coding section. Okay, so here I want to show you some mathematical modeling of different things. So first thing first, so let us just keep the cost function for later. It is just that whatever the grid gives us at a given time, I mean the price that is decided by the grid, then the factor that we buy, the amount that we buy, it will become our cost. So the overall objective function will become the sell minus buy. So here, to keep it positive or to keep it profitable, we have to sell more and buy less. Somehow we have to manage everything such that the cost function gives us the profit. So let us discuss the modeling of EV here. EV is being here charged, so we are actually checking the state of charge of our EV at a given time. That says that we have our EV at some previous time, t minus 1, then when it receives some energy, that means we add that energy to it, and that energy is this charging energy that we are charging. If we are discharging, then this is the discharging energy, and the equation is simple, that when we are charging, we multiply with the efficiency factor, and when we are discharging, we divide it with the efficiency factor. This is the standard formulation of the charging, battery charging. We are not using any complex aging factors or other things here. Overall capacity of the EV will be used to keep the SOC between 0 and 1 overall. So we define some constraints for charging the EV here. I will show you the equations. I will show you the codes related to these equations. So here we have these constraints of time, that at a time we can only charge or discharge the battery. I mean, either we will charge or we will discharge. We cannot charge or discharge at the same time. And it is assumed that in the equation 4, it is assumed that when the time at which the vehicle departs, its energy is more than the time at which the vehicle discharge has some difference, or it is beyond the time of that time at which EV arrives. So these are the basic constraints that we will be using here for the EV, and somewhat similar constraints will be used for the battery. Let us first discuss this battery part and the EV part. Here in our code, here is our battery module. This is a story. Let me just close it. So difference and save changes. Okay, so the battery class, it is an object-oriented class. So here we have this size of the battery and eta, the efficiency factor here, eta from this here eta is input, so that we can charge or discharge at different efficiency factors. And I have kept it 0.95, 95% efficiency of charging, and 5% loss due to some reasons. So what the charging here is, we can see that if we have some energy coming, that is storable energy. So that is the here. So energy is here, that is coming from the for the charge. Let's say we say that X amount of energy will be charged at time t. So how this will be charged? First of all, it will check that if the battery is full or not. So if the battery is not full and the battery status is not full, these both are the same, almost same. But these two conditions are checked here to keep the model in such a way that we do not go into the charging and discharging states simultaneously. Because if a battery is under charge, that is the state 1, if battery is under charge, so it may not discharge if it is not full. So status tells us that if the state of the battery is either under charging or discharging. So what we do further is that we assess the amount for which we have to charge the battery. Here we say that if the battery SOC is 1, total SOC is 1.0, as we have normalized here with the overall capacity of the battery. So it is, if it is 1 minus the current amount of charge available inside the battery, so we get the storable here, and then we multiply the storable. That here it is actually the condition. We are checking the condition in this equations. We are checking the condition that if the energy incoming is actually can be stored. So this is the required energy, this is the incoming energy, and then we charge this energy according to the equation. That is, we multiply it with the eta and divide it with the size. This will give us the SOC at t plus 1 or SOC at t, and this is the SOC at t minus 1. So we have done this through plus and equal at the simultaneous. Here we have done something interesting in such a way to actually handle some bugs, because if we directly store this energy inside the battery might not be able to fully save that energy. So to avoid that condition, we are just checking this required for storage variable. If this variable is not fulfilling, if this condition is not fulfilling, what we do here is that we just keep the energy that is required. So here one thing is interesting, that we just keep the energy that is required, and that means at this stage the battery will get full, because there is only required energy for storage is lesser than the actual energy incoming for storage. So we will change the status again. We will change the status. Let's check. Yeah, still it is under charging. We will change the state later in next step, because in this step it is still under charging. So we keep this status 1, and then what we do here is that we see that this much amount has been curtailed. So either this is wasted or it can be returned to the agent back for further utilization of the energy. So this will actually keep our balance of energy in this state, in such state. Now if we see this overall condition here, that if the SOC is not less than 1, that means the SOC has the battery is full. So at that we give the state 0. That means we can now discharge it. And other things, if we want to keep the curtail amount, and if we want to get the SOC plot and time step, if we are just using this battery module independently, we can just uncomment these variables for our usage later. Next, we move to this train function. We have discussed in this equation two things. This is the charging part that we have covered. Eta multiplied by eta divided by capacity. But in the coding section, we do few things more. Why we do few things more? Because we have to check about various things that can occur in the coding which are not presented in the theory. And yes, we can also present those in the theory as well. So let's say we have to drain some amount of load. It is also energy, but when we drain, we call it load, and when we charge, we call it energy. For the sake of convenience, you can call it energy or load. So reset this variable, then check if battery state is equal to 1. That means battery is under charging, so we cannot go into this discharging and we just go outside this loop without returning anything or without doing anything. So that will be linked to this what we have here, that charging and discharging should not be at the same time. So either it can be charged or it can be discharged, but it cannot be charged or discharged at the same time. And further, there is one more condition, that is to operate the battery in safe operation rating region and to save it from one function. So this is this charging and discharging condition. This is discharging and discharging condition here. Yeah. So we cannot go beyond the minimum and cannot go beyond the maximum. So we set some minimum limit so that we can just avoid the dead state of the battery. Because practically we do not discharge the battery to the last point of energy it has. For that purpose, what we do here is that we just keep some SOC safe. That is 20% of the SOC will be kept to avoid dead cycle. This will enhance the battery life. So in coding, we do it in this way, that we just keep the 20% condition and check that if it's greater than or self-dot status is equal to 1. So here it is just like a coding issue. I have just coded it a few years ago and I was not that much coder at that time. So I just keep on introducing variables. So this variable is introduced for the status thing that states that the variable that we are in the discharging state. So here we check that if the state of the battery is now it is under discharging, so it cannot be charged. If the state is equal to 2, it cannot be discharged. So now we get the dischargeable amount. Once the dischargeable amount is obtained, then we again, this is the load divided by the size divided by the eta. That gives us the actual amount that we are going to charge. Here is the load divided by eta divided by the overall capacity of the battery. This is the discharging part that we have done. So in this whole class object of the battery, we are doing this equation number 9 here in this setup. Moving further, if we see both of these equations, the battery storage and the EV charging equations, both are the same. The difference is between a few of these constraints, but constraints are also same because EV is also charging, and we can consider the EV as a battery because we are just charging the EV. here. So you will see the similar functions and similar variables being computed in this way. We have just introduced our battery function and this EV charging and discharging function. Now let us move towards the photovoltaic generation. So photovoltaic generation, we can simulate this data as well, but using realistic data is better. I have used the data set here. You can check it from the paper. The data set that I have used, I have given the details of the data set in the paper. Here PV is just a variable here. Yeah, you cannot see it here, but the PV is here. PV is just a variable here, that is at a given time we just get this PV for us, photovoltaic generation for us. So to get this photovoltaic generation, what we do here in this class, this whole class, let's zoom in so that we can see it properly. So this PV class, guys, has this data set, and from this data set it is getting this solar variable from this data set. This is a what we say CSV data frame. Yeah, what we say CSV data frame. You can see it is a CSV data frame just with the 4416 values, and that's it. So I am dividing it with the maximum value available in the data set, that is normalizing the solar values. The benefit of this normalization is that we can just enhance the capacity as per our demand, that is 20 kilowatt solar here, and we can just change this 20, 30, 50, whatever building we are using, so it will be tailored according to the building. And but if you are using the weather conditions, then this data might not be useful in any in other building, in other areas. But if you are using the concept of just energy optimization and energy management, then you can easily use this same function, and you can just use that function for the overall setup, for overall PV setup, because the PV peaks are similar for every region. That is, when there is sunrise, there will be solar generation. When there is sunset, then there will be no solar generation. That's just a rule of thumb. So what we did is that we just got this data set in a variable, and then we just defined a function here. This method actually calls this time step. At any time step t, we just get this value from the PV data set and divide it by 100 to convert it to like kilowatt. So similarly, the price data set comes here. I have used different price data set, one price data set, but we can use one data, any data from this price data set. And actually I have used one data, I have declared two data because there were two prices, so I just tailored it according to my needs. You can tailor it as per your needs, and the same data set is available for you, and you can use that data set. Here I have just tuned the data price accordingly so that whatever price is realistic, I can get that price. So here you can say that why I am just tailoring it or tuning it in this way. The reason behind this is that actually the real-time data from any data set that is realistic, I have used realistic data set from some European website. So that is realistic. It gives us the trends that are actually present in the price with the generation and with the time of the day. So when we have the trends, actual trends of the price, then we can actually use those trends to model our own price models. This is a pricing model for our system. EV schedule is just a schedule. Basically, we say that when a person is at home, it is usually in the office from 8 to 4, let's say, and it is at the person is at home around 6 to 11, 6 to, let's say, sorry, 6 to 8 a.m., 6 p.m. to 8 a.m. So for in that range, we can, in that time frame, we can just charge the EV. For further adding the dynamics, we have added some dynamic in this data set. This is somewhat modeled data set, not actual data set. So modeled as per the intuition of the EV being at home. So let me tell you that, let's say a person is at home from 6 p.m. to 8 a.m. And not at home from 8 a.m. to 6 p.m. simply. So it is just the way around. But what we have did here is something amazing. That a person might go shopping or may not be willing to charge EV at any time. So this is what we have also included in this data set. So you can use also that you can tailor this data set as per your need. But this data set is what that I said. So if you have any questions or anything, yeah. So I will go with this explanation. I will keep your questions, but I will answer those questions maybe in some other session. But mainly I will explain the code here. So this is how you will model the electric vehicle schedule. Later, let us come to the appliances here. Here we see that we have different appliances: washing machine, lighting, microwave, refrigerator, dryer, air conditioner. These are different appliances that we have here. So what these appliances apply in equation 14. These appliances say that the model says that at any time each appliance each appliance has some load. So whatever the load is, we will sum it up for all the appliances and we will present it as a single load to the agent, overall load. In this way, so to model this equation 14, what we did is that we got this data set, dishwasher, data set, cloth washer, dryer, and all that other data set. And there are other appliances in the data set, but we are using some specific appliances, maybe 4 or 5 or whatever appliances that you can use. Just normalize the data set to get the trends, the actual trends of some region from the data set. This is the actual data set. So this is actually something realistic. Other than losses in the system, so everything else, it is all about scheduling. So that's why we just mainly focus on the trends rather than internal losses or other things. So we are mainly focusing on the trends. For that, we are just taking some data set, taking their patterns and then making them something realistic in terms of energy consumption. To make it realistic in energy consumption, we are multiplying this kilowatt factor, that is 1.2 kilowatt usually for dishwasher, 1 kilowatt usually for washing machine, 3.5 kilowatt for cloth dryer, and 3.5 kilowatt for HVAC. Somewhat similar from the internet. I got this somewhat standard energy ratings for these different appliances. Now that we have initialized these trends, what we will do? We will just get the load for a given time step t. At a given time step t, we just sum up all the available loads and divide it by 100. That means we will be using kilowatt unit overall in the system. So this all class models equation 14 from the paper. Now this equation 15 is actually the objective. Objective here is to just balance the energy. First of all we will balance the energy. How we will balance the energy? Let's say P by, that means power that we obtained from the grid. Then we discharge some energy from the batteries. That means these energies are available at home, so we add those. And if we charge some energy to the battery, that will be subtracted. And if we discharge the EV, that will also be added. If we similarly, load will be subtracted, cell will be subtracted, charging will be subtracted for the EV, and then PV will be added. So overall, the energy is coming to the home either from the battery or from the grid or from the PC will be with the positive sign, and the energies going out of the system, fulfilling the load, charging the batteries or charging the EVs, so charging the EV will be actually with the negative sign. So when we sum all those up, that must be equal to the power demanded. That actually balances the whole power, and actually the power, it must be zero at any given time, because we have buy and sell and all that thing. So power demand sometimes is zero. Theoretically, it is theoretically not actually zero. It means like the overall sum of all the energies coming to the home and going out of going into the appliances or going out of the home must be equal. Sum of all the energies must be equal. So this is the overall objective. So we can just test this home model here, and we can just plot our refrigerator pattern, air conditioning consumption pattern. These are all the consumption patterns. Okay, so now let us come to the home model, actually overall home model. Now before coming to this home model, let us discuss this home model in terms of functions. Before then we will discuss this MDP model for reinforcement therapy. So far we have just made individual models of the appliances, the solder and all the things. Now we will make a new object. New object will be this class home environment. You can name it anything. And we say that, just a second. Yeah. So we here define that this EV charging capacity, we have taken it from the standard. This is the kilowatt. Actually, kilowatt hours. So overall, 7.4 kilowatt hours of energy can be saved inside the EV. This is somewhat standard in Tesla EV, Tesla electric vehicles. So to model this, first we have defined the objects for different models that we will be using individually in our system, which are these appliances model, energy storage model. I am not shown the grid model. Grid model is basically simple that come inside the home model. We will check that out. This is the PV panel. All has been modeled, and these are data driven, so these we can consider these realistic, actually realistic, because this is based on the actual real world data set. So let us come to the models with so many variables here. We will just keep an eye on the major variables. Other variables are either to control the flows or to just log the history of different things. The names are kept clear so that we can understand exactly what it is. So we have just make an instance of the PV. So our solar is in our home. Then we have this EV schedule, price data, batteries, EV and appliances. Everything that we have defined here is now in our home here, overall home model. Other models we will be seeing in further. So we need to initialize some models in some variables earlier, so that we can just reset those variables. Now that I have made a reset function, I think whenever you code, just make a reset function there, so that reset function takes you at some initial state where you can just say that now I am at an initial state. If I want to move further, what changes I expect and what changes I see, that this will just keep you in touch with, keep you like properly informed about your system behavior. Before moving further, just an add-on for you guys, that whenever we see a paper, we see equations in that, just get the intuitions from those equations, and whatever you get from those equations, just generalize it in your mind, make a flow of that, and then try to make a logic from that. When you have logic in it, the logic that it has inside that, then you can just easily manage that thing. Yeah. Okay. So here I think, as per my understanding, that I have to reset my EVs, so that I am at the start at the zero charging state of EVs, at the zero charging state of batteries. Then any battery, so you see that we have total batteries here, I guess 3. The total batteries here 3. We have these 3 batteries in total. So these 3 total batteries here, so yeah, we reset the batteries. That's why we have some battery number. That battery number 1 is being charged, battery number 2 is being discharged, battery number 3 is idle. So like that, we have to keep the numbers so that we can actually charge the batteries one by one and keep all the batteries charged. Previously, we have just defined the charging discharging mechanisms. We have the charging discharging mechanisms. Now we can have multiple batteries, 1, 10, 100, 1000, whatever count of batteries you want to keep. You can just initialize that, then control that, plot that, whatever you want to do individually, you can do with that. So here drain number is actually drain number and battery number charging for charging, drain number for discharging, and then charge count. So different variables are kept here. Then this log data set is reset in this method. Now this there comes to the main energy method, that is our main method that gives us the energy and the load. So what we say here is that, let's say if we have some generation at a given time t, and we have some load at a given time t, and we will see from what t is here and from where it is coming. I will show you that also. Generation here, load here, so we just keep track of the generation and the consumption here. Then we say that if the generation is greater than load, this is simple intuition that if generation is greater than load, then we can just subtract generation from the load and keep the energy positive. And if the load is greater than generation, then we just subtract the load from the generation to keep the energy variable positive, so that whenever we give it to the system, it actually subtracts or adds as per the equations defined here. Otherwise the signs will be reversed and we have to do some very different logical mathematics that will complicate the things. So far so good. So then now what we have is that here energy. This energy is after fulfilling the load or having the remaining, and this is the generation function. So get load function actually gets that appliances. Now let us do the save battery function. Here we are just discharging the batteries one by one, where I say that if from the set of batteries, if any battery has any battery is not fully charged, then select that battery and just charge that battery. Okay. So I am using the OR condition so that we can, if any of the battery still has to be charged, I will select that battery. That battery number will be I will be just rounding it off from the zero, starting from zero, because initially it was zero. So I will charge that battery. That is interesting that we have these batteries and we just using this charge function. My question to you is, from where this charge function I am using? Answer is simple, but maybe for the new coders, maybe a point to think. Now we have given the amount of energy that it has to charge and the time step for which we are so that we can keep track of charge energy with respect to the time variable also. So for any battery that is full, what we do, that we check for the curtail amount, because we have defined some curtail amount in the battery class. So we get that curtail amount, we use that curtail amount in the next battery. In that way we just are saving the actual energy. We are not leaving a bit of the energy behind, or we can say a fraction of the kilowatt. We are not just wasting that any energy. So in this way the energies will flow properly. These kind of conditions come in code with a little bit difficulty and logic. So you have to keep track of these kind of logics to avoid any glitches or any, I would say, bugs in your overall logic. When we see the graphs, we see some different things that we don't want, we are not expecting here. Those are because of these kind of I would say maybe missing points or something that lags behind. So we charge that extra amount of energy or curtailed amount from the previous battery to the next battery. Here we just change the battery to the next battery if that battery is not charged. So this for loop is actually changing the battery number, selecting the next uncharged battery. Either it is 0, either it is next to the 3, either it is 3 or it is 2. So it is not always 0, 1, 2, 3. It is not always 1, 2, 3. It can be random based on the state of the battery, being charged, being discharged, undercharging, discharging. In all these scenarios, because we are covering those step by step, so this is the beauty of the object oriented programming here. Maybe a bit boring because I am just explaining the code and just going through the code. If you are taking interest in this code, it will be very, very good for you further evaluate the code and further see the code. And if you are getting bored, just see these cats, catties, and this crab and other dog is coming later. Okay, so my sense of humor is also okay. So this battery number here, it is also an interesting function here for changing the battery number. It actually checks here that all the batteries are charged or not. Let's say if all the battery status is 1, that means all the batteries are full. So this will take the battery number to 0, and it will never come to it will always break because and do nothing, because all the batteries are full. Even if you will save the energy, it will do nothing. And if we drain from the battery, any of the battery must be full. So if any of the battery is full, we can check that the status of that battery and states of that specific battery and discharge it for our purpose. Here we are draining the energy, and here we are just switching the batteries based on the battery under discharge. Here in this loop, mainly we check if the status of the battery is empty. That means we have to change the battery. For that purpose, we are just going through the batteries, checking their status, and just selecting the drain number accordingly. Whatever battery is empty, we will choose that state number. Okay. Especially if someone is asking that what scenarios is the RL approach especially strong or weak. I will come to this point later, and we are at the initial stage of this explanation here. Let me just go one by one, and at the end we will check out the paper, we will check out the matrix, we will check out the realistic conditions. I have done various interesting things in the paper, and you can just various interesting things in the paper, and I will show you later as I move further. Now that we have selected the battery that actually has some charging in it or some energy in it, so we can drain the energy and then save it for our purpose. And we say that this is something that we have assumed as a profit, because the batteries are being charged from the PVs only, not from the grid. So whenever we will discharge the battery, we are saying that we are discharging it because we are not going to buy at this time. Because we are not going to buy at this time, that's why we are earning the profit. if we will not discharge the battery, we will buy some energy to fulfill our load. And if we will buy some energy to fulfill our load, that means we have to pay the price. That will be the cost. But if we are discharging from the battery, that we are earning the profit somehow. So we are considering it a profit for the RL, so that RL can consider it as a profit. Okay, moving further. Similar function here. As per the charging, we are just discharging. If all the batteries are discharged, we cannot discharge any. Now this method manage energy is actually managing the energy through a conditional. That is the baseline of this research. In this method, what we do here is that we take the generation, take the load, and just get the energy. If the battery SOC is less than 1, 1, 2, 0, 1, 2, any of the 3 batteries has SOC which is less than 1, what we do is we save some energy. That energy is after fulfilling the load. So we are first priority is the load. That means the consumer's comfort is the first thing. Then we save the extra amount of energy, and even if all the batteries are full, then we can also charge the electrical vehicle. So, and if the electrical vehicle is also charged, then we can export the energy. In this way, we can say that if we have excess energy in the system, that means the first priority will be given to the batteries for charging. The second priority will be EV, and the third priority will be export. In this if and else loop, we are just setting the priorities. So whatever priorities you are interested in, you can set it accordingly. It is just conditional, the baseline controller. So my objective of the paper was to first save some energy for night, and also for charging the EVs. So I just save the energy in the daytime first of all, then I charge the EVs later, and then I export the energy. Let us come to this condition here when we say that we are charging the EVs, but we check that if the energy is greater than the energy charging capacity, because at less than 7.4 kilowatt you cannot charge. If you do not have this much threshold, you cannot charge the EV actually. So we have to get that threshold of the energy. Then and keep charging until the EV SOC is not full. And also if EV is at home, so at a given time, if EV is at home, I will just change it somewhere to 0. It is actually 1, and this is also 1. So let us move further. Let us move further here. Now that if the system load is higher and the generation is less, the volume is a little bit low. Let me enhance the volume here. Okay, so if the energy is if the load is higher than the generation, that means we have to drain from the battery, and we cannot charge EVs. So far we will go like this. and if the EV status is less than 80% and we have to charge the EV, then we will just discharge from the battery and charge the EV. Similarly, if we do not have energy at home, we can get it from the grid, and if the EV state is less than 80%, we have to charge the EV at the very first priority. So these two conditions, the first condition is that we have excess energy at home, and the second condition is that we have low energy at home, lesser energy at home. In that state, we are actually draining from the battery and charging the EV. And if we are this is just a test function, this is not a useful function in here. Okay, so get from grid. In here, if we use this get from grid function, we are actually it is costing us something. That is the cost of the price at a given time. So we are taking that cost here and considering it as an import. And similarly, if we export, that means we are earning some profit here. And this is the EV charging function here. EV charging function is exactly the similar. And we also say that if we charge the EV at a given time, we just earn some profit. Because we are charging the EV from the home batteries, so that we do not need the solar or other things. And that means we are charging the EV from the renewable energy, that is solar, not from the grid. So that means we are also earning profit from by maximizing renewable energy usage. All right. So this is a bit complex function that actually takes in three things. First thing is that if the gen load is equal to 1, let us see what it is. Gen load is equal to 1. So here we have just got this gen load is equal to 1. That means we can go inside the EV charging state without checking the battery. So if that means if gen load, that means we can just charge the battery up to 7.4 kilowatt, and we can earn that profit, and that profit can be saved to the EV profit. Similarly, if the energy is greater than EV charging, if the energy is equal to EV charging capacity, and if the energy is greater than EV charging capacity, then we are just charging the EV as per the EV charging capacity, and the remaining energy is there. And if the energy is less than EV charging capacity, we are just charging, because as I said that we just need to keep our EV charging to a specific level. We have to provide some specific amount of load to the EV for actually charging the EV, otherwise EV will not be charged. For that purpose, what we did here is we just accomplished the full energy at that given time. Here you will see that we charge the EV. If there is remain, that will be costed us. That will be our cost, because we have to get this from the grid or somewhere else. So that we can charge the EV with the full potential here. So what we did is that whatever we gave the EV, we consider it as a profit, and whatever we obtained from the grid, we consider it as a cost. So the overall profit become our personal profit and the cost to the grid. So on the other hand, if we have some amount available in the batteries, we can drain it from the battery, and we can also get from the grid if we have to charge the EV because EV is our first priority here. Whenever EV is at home, it is our first priority to charge. So we just make this profit negative so that we can just consider it as a cost rather than a pure profit. So this manage energy is the similar function. Yes, yeah. So that's it. That's just some extra piece of code here. Otherwise, the explanation is complete. Now, yes, we are moving towards the plots. Yeah, here we see these battery states. Battery states are either charging, discharging, or idle. So these three states are given here. Clearly, we can see in the time frame that sometimes it is first charging, then go to the idle, either charging, either idle. So we can go from the idle to the charging and idle to the discharging, not from the charging to the discharging directly. We will not see any jump from the charging to the discharging here. Rather, you will see the jumps from the idle to the charging or idle to the discharging like this. So this here graph is actually plotting everything. This is the conditional, I guess. So here we see the batteries. It is the overall battery. As you see that battery is full. So first of all, in first few hours, our battery is full. But EV is not at home. EV is at home at some 600 hours. So sorry, at 6 p.m. and at that time, here are the days. Yeah, at that time, when EV comes at home, stays at home for some time, and we just schedule this. At this point, EV has been scheduled for charging, and this is the amount of energy that is being given to the EV for charging. So EV is charging step by step, either from the battery, it is charging from the battery, so battery SOC is decreasing accordingly. Similarly, whenever we charge the EV is at home, we saw that it is less than 80%, so we just discharge the battery and discharge the EV, even though it was in the night time. And it is also in the night time, so this is how we just charge or discharge the EVs. Now that we have actually explained the home model and all the model, now let us come to the deep reinforcement learning model. Before going to the actual model of our home, I guess this deep reinforcement learning session, let us have some break for here, and 10 to 20 minutes or maybe a day tomorrow I will check it out and I will update this later. Again, just for the electric vehicles, just let me answer few of your questions first. So basically we are seeing three things here: generation, load, export, import, charging and discharge. These all things are being seen simultaneously. We are comparing some random decision making, some conditional decision making, and RL agent based decision making. And then we have different case studies in it. In these case studies, we are using different amount of energy in the solar panel and as a load. So these three case studies are compared here to actually satisfy the I would say, the generalizability of the reinforcement learning agent. We have done these 3 case studies, and main thing we are seeing is the profit that we are making, so that we can just check if the agent is actually making some profit or not. And simultaneously we are seeing that if the EV is being scheduled, when EV is at home, and it is being scheduled or not. So here we just are monitoring 2 things: the EV SOC and the energy. Whenever EV is at home, it is scheduled if the energy is less than 80%, and if its energy is not less than 80%, it is not scheduled. These type of things are being observed here. So thank you so much for being with me so far, and I will update further inshallah very soon with the reinforcement learning part. And if you are interested in the reinforcement learning part, just comment. And if you find this video interesting for you, just subscribe this channel for more such videos and explanations of the code. Similarly, if you have something interesting that you want us to explain, just let us know. We will explain it right away. Thank you so much. Allah Hafiz.